Hi. This lesson is on more Cartesian vectors and operations with vectors. So our learning goals, we're learning to write an algebraic vector in two ways. We've already looked at ordered pair, triple, and we're also going to look at it as a sum of scalar multiples of vectors I hat, j hat, and k hat. We're learning to find a unit vector given an algebraic vector. We're learning to determine whether or not a vector is a unit vector. And we're learning to find the sum or difference of algebraic vectors. We're learning to find the magnitude of the sum or difference of algebraic vectors. So we've learned that an algebraic vector can be written as an ordered pair or triple. Algebraic vectors can also be written as a vector sum of scalar multiples of the unit vectors I hat, j hat, and k hat. So our first example says to rewrite the vector v equals 3, 5, which remember it's an algebraic vector, so its starting point would be 0, 0, and its ending point is 3, 5, as the vector sum of scalar multiples of the unit vectors I hat and j hat. So first I'm going to draw this vector, so we know its starting point is at 0, 0, and its ending point is at 3, 5, and in 2 space this is the x-axis and the y-axis. So there's the ending point there. And then we can draw in this vector. So there's our vector. This is vector v. And we could also think of it as a vector made by adding 3 vector I hats. So remember, I hat is a unit vector in the positive direction of the x-axis. So this would be an I hat right here. And then this vector from here to here, starting at 0, 0 and ending at 3, 0 would be 3 I hat. And then on the tip of 3 I hat, we can add 5 j hat. So again, this would be like 1 j hat, and 5 of them make 5 j hat. So another way of writing vector v using a vector sum would be that we can say vector v is 3 I hat plus 5 j hat. So these are two ways of writing the exact same thing. They're both algebraic vectors that start at 0, 0 and end at the point 3, 5. This is the notation you'll most often work with just because it's easier to write down, okay? But you should realize that these are equal. These are both saying the exact same thing, okay? All right. Now we're going to move to 3 space. So rewrite the vector u equals 3, negative 2, 4 as the vector sum of scalar multiples of the unit vectors I hat, j hat, and k hat. So we're also going to just practice drawing vector u, and so I can show you where the I hat, j hat, and k hat vectors come in. So we learned already that when we have just vector u in this format, these represent, that's the x value of the corner of the vector, the y value, and the z value. And when we go to draw it in 3 space so that it looks like it exists in 3-dimensional space, we like to draw it in a box. So, and my way of drawing that box is to start off with using the y-axis and z-axis. So in 3 space, the x-axis comes out of the page, positive x-axis, and into the page is the negative x-axis. Positive y is to the right and negative y is to the left. Positive z is up and negative z is down. Okay, so I'm going to take my y at being negative 2, which would be over here, and my z at being positive 4, and then go up, and starting at 0, 0, and then I'm going to form part of the box that my vector is going to exist in to make it look more like it's in 3-dimensional space. So I've used up kind of the y and the z, and now I use the x. So the x is positive. So starting at 0, 0, I'm going to come 3, 1, 2, 3 out here. And that's going to be a corner of my box as well. And then, so from here, I'm going to go negative 2 in the y direction, So I'm going to count them over. It won't be perfect, so it looks like it's a little outside of this corner. So 1, 2 over here. And then I'm going to go up 4. 1, 2, 3, 4. And same thing here. 1, 2, 3, 4. And then I'm going to make, in this case, the front of the box. And then to finish my box, I'm going to join the corresponding corners with a ruler. And then this one goes along the x-axis. So there is my box drawn. This one's hard, it's hard for it to show up. Okay. So I know that starting at 0, 0, 0, that's going to be where my vector starts. So I'm going to use, I guess I'll use green. So my vector is going to start here. There's its starting point. And then it's going to go 3i hat. So in the positive x direction, 3 along the x-axis, and then -2 in the y direction, and then up here. So that its ending corner is going to be there. And then I can draw this vector in using a ruler. It's going to go up to that top front corner of the box and put an arrow on it to show that it starts at 0, 0, 0 and ends at the point 3, -2, 4. And this is vector u. Okay? And then I'm trying to show you that we could also write vector u using ordered triple, or no, sorry, that is using ordered triple, so this is an ordered triple. We could also write it as scalar multiples of I hat, j hat, and k hat heading together. So 3i hat minus 2j hat plus 4k hat is another way to write that vector. And again, 3i hat would be this here, that's 3i hat, followed by adding on -2j hat, and then adding on positive 4k hat. So 3i hat minus 2j hat plus 4k hat gets you to that same point. So again, 2 equivalent ways to write it. And this one is writing it using the vector sum of scalar multiples of units of I hat, j hat, and k hat. Part B says find u hat both as an ordered triple and as the vector sum of scalar multiples of I hat, j hat, and k hat, and add it to the sketch. So u hat, by definition, is going to be vector u divided by the magnitude of vector u. That's the formula for a unit vector. So I'm going to start off with ordered triple for u hat, which is 3, -2, 4. And then we also need to find the magnitude of vector u. So we can do that by the sum of the squares, square root of the sum of the squares of the components. Remember, you can put -2 squared here, but you don't need the negative because we know that when we square a negative number, it's always going to be positive. And as you do this over and over again, you'll find that you're able to do that. So I'm just going to add the squares. So it's going to be 3 squared plus 2 squared. I don't have to involve the negative because I know when I square a negative number, I'll get a positive. And I get square root of 29. And then I'm going to come up here and then divide each component by the square root of 29. So 3 over the square root of 29, -2 over the square root of 29, and 4 over the square root of 29. So that's written as an ordered triple. So I'm going to collate those with green highlighter. And then I also want to write it as the sum of scalar multiples of I hat, j hat, and k hat. So I could also write u hat as 3 over root 29 I hat minus 2 over root 29 j hat plus 4 over root 29 k hat. So this is being written as the vector sum of scalar multiples of I hat, j hat, and k hat. And they mean exactly the same thing, just two different ways of writing it. Just of note here, this isn't a thing, so you can't write u hat equals 3 over root 29 I hat, comma, negative 2 over root 29 j hat, comma, 4 over root 29 k hat. That's not a thing, okay? So you're kind of mixing the two notations together. So it's either an ordered triple, or it's as a vector sum of scalar multiples of I hat, j hat, and k hat. It's not any kind of mix there, one or the other. Okay, so two different ways of writing the same thing. Adding it to the sketch, it's one unit in the direction of the green vector. So if I want to try to do it as exact as I can, I could measure how long a unit is here, and it looks like it's 1, 2, 3, 4, 5, 6, 6 little ticks on my inch there. So I could line that up, 1, 2, 3, 4, 5, 6 with my 0 here, and just go along this vector to there. It's got exactly the same direction. Starts at 0, 0, 0. It adds 1 unit along vector u, and I can call that vector u hat. Adding it to the sketch. So rewrite each algebraic vector as a linear combination of I hat, j hat, and k hat. So this is just changing notation from either an ordered pair or ordered triple to this sum of scalar multiples of I hat, j hat, and k hat. So in this case, I would say vector u could also be written as negative 2 I hat plus 4 j hat. Here I could say vector u could be written as negative 2 I hat plus 4 j hat. Okay, you can see that these both look identical. So here, if this was one of your vectors, you'd know you were talking about 3 space, and here you would know you were talking about 2 space, but writing them in terms of I hat, j hat, and k hat, you can't tell that in this case if the k component is 0. In this case, vector u is negative 2 I hat plus 0 j hat, which we wouldn't need to show, plus 4 k hat. Vector AB can be written as negative 3 I hat plus 4 j hat plus k hat. Vector V, 0 I hat plus 0 j hat, just minus 5 k hat. And vector OP would be 0 I hat plus 3 j hat minus 3 k hat. Rewrite the following vectors in ordered pair or ordered triple form, and it will tell you. So write vector v equals I hat as an ordered pair. So I hat is the unit vector for the positive x-axis, the coefficient's 1, so 1, 0 would be the ordered pair. Vector u, written as an ordered triple, would be 2, negative 3, negative 1. And it wants us to write vector AB as an ordered triple. So as an ordered triple, it would be 3, negative root 2, 0. Example given, vector v is negative 2 I hat plus 4 j hat minus 3 k hat. Determine v hat both as an ordered triple and as a linear combination of I hat, j hat, and k hat. So we're finding a unit vector in the same direction as vector v. Probably first thing I would do is rewrite vector v as an ordered triple. And then I would use my formula for finding the unit vector v hat, which is vector v over its magnitude. So that's negative 2, 4, negative 3 over the square root of 2 squared plus 4 squared plus 3 squared. Its magnitude. So that's going to be 1629 So vector v hat is going to be negative 2 over root 29, 4 over root 29, negative 3 over root 29. And that says an ordered triple. And then we could also write it as a linear combination of I hat, j hat, and k hat. And we could write it as negative 2 over root 29 I hat plus 4 over root 29 j hat minus 3 over root 29 k hat. And our next example, is this vector a unit vector? So to say whether a vector is a unit vector, it's a really easy method you can always use here. Is its magnitude equal to 1? So that's how you're always going to test if something's a unit vector, is its magnitude equal to 1. So we can find the magnitude of vector u. So I might want to rewrite it first as a ordered triple in this case, a half, negative a quarter, negative a quarter. And now I'm finding its magnitude. So it's going to be the square root of a half squared plus, I don't need the negative, but I can include it. Okay, so now I'm squaring a fraction, so I know that I square the top and square the bottom. So 1 squared is 1 over 2 squared, which is 4, plus 1 over 16, plus 1 over 16. So the magnitude of vector u is the square root of, so I want to have all denominators being 16 here. And then 4 times 4. So that's going to give me the magnitude of vector u is the square root of 4, 5, 6 over 16, which we can tell is not going to be 1. So that's going to give me the square root of, divide top and bottom by 2, 3 over 8, which does not equal 1. So therefore, vector u is not a unit vector. Okay, so if you find the magnitude of a vector and it turns out to be 1, it is a unit vector. If you find the magnitude of a vector and it doesn't turn out to be 1, it's not a unit vector. So algebraic vectors can be added and subtracted very easily. So for example, if I have vector u, which is 2, 3, so I'll draw this one in orange. So it starts at 0, 0 and ends at 2, 3. We're in 2 space right now. I can draw my vector u. So there's vector u. And I can also draw vector v, which starts at 0, 0 and ends at 3, negative 1. So here's vector v. And if we want u plus v, we can go back to our geometric definition. So we can take vector v and move it to the tip of vector u. But we can see vector v starts at 0, 0 and we go to the right 3 and down 1. So from the tip of this one, we can go to the right 1, 2, 3 and down 1, replicating vector v there, but putting it at the tip. So this is vector v, we just moved it. And then u plus v vector is going to be from the tail, from 0, 0, from the tail of vector u to the tip of vector v when they're added. So here, this is vector u plus v, which we can visually see that vector u plus v is going to be 1, 2, 3, 4, 5, 2. But the really cool thing is we don't need a diagram. We can take vector u, which is 2, 3, and add vector v, which is 3, negative 1, and add the corresponding x components. 2 plus 3 is 5, and the corresponding y components. 3 plus negative 1 is 2, and vector u plus v is 5, 2, just like we proved it was with the diagram. Okay? Similarly, we could do that. So let's do first the calculation for v minus u. So vector v is 3, negative 1. And we're subtracting vector u, which is 2, 3. So we can subtract components. 3 subtract 2 is 1. Negative 1 subtract 3 is negative 4. So there's our prediction that vector v minus u is going to be 1, negative 4. But we can come over here and do vector v and subtract u. So if u is 2, 3, then negative u, I'll do that in pencil, negative u is going to be negative 2, negative 3. So from here I'm going to go 2 in the negative x direction and then down 3, and that should give me negative u. So here's negative u being drawn there. And I'll get a different color here. So this vector I'm drawing from 0, 0 to this tip here is going to be vector v minus u. And we can see from our diagram here that vector v minus u starts at 0, 0 and ends at 1, negative 4, which is exactly what we got when we just subtracted our algebraic vectors. And then the magnitude of u plus v. So the magnitude of u plus v means they want the magnitude of this vector 5, 2. So the magnitude of the vector 5, 2. So watch notation here, how you write it down, how you communicate it, which is the square root of 5 squared plus 2 squared, which is the square root of 29, 25 plus 4 units. So that's the magnitude. So this is a vector, this is a vector, this is a number. The magnitude of a vector is a number. So this gives us some rules here. So if vector u has an x component u1 and a y component u2, and vector v has components v1 and v2, then vector u plus v will have component to u1 plus v1 for its x, and u2 plus v2 for its y, and that just extends right into 3 space. So you add the corresponding x components, add the corresponding y components, and here u2 plus v2, and add the corresponding z components. So here we have a question. If v equals 1, negative 3, 2, so we're in 3 space now, and w equals 4, 7, 1, then find v plus w. So v plus w is going to be 1, negative 3, 2, plus 4, 7, 1, which is going to be, so 1 plus 4 is 5, negative 3 plus 7 is 4, 2 plus 1 is 3. So that's vector v plus w. Vector v minus w, so vector v, 1, negative 3, 2, subtract vector w, is going to be vector 1 minus 4 is negative 3, negative 3 minus 7 is negative 10, 2 minus 1 is 1. And then part C asks for the magnitude of vector v minus w, so it wants the magnitude of this vector we just found, negative 3, negative 10, 1. So that's how you would write out your first step. And then to find the magnitude of a vector, it's the square root of the squares of the components. I'm ignoring the negatives because I know when I square a negative number, I'm going to get a positive. So that's going to be the square root of 110. And that's going to be the magnitude, or the length of vector v minus w. All right, so if vector w is negative 2, 4, so let's do a picture of vector w. So negative 2, positive 4 starts at 0, 0. So that's vector w that I just drew there. So 2 vector w is going to be twice as long. Okay, so if I draw a vector w twice as long as this one, I'm just going to go over 2 and up 4 again. And then I'll use a different color here. So from 0, 0 to the tip here in pink, this whole vector here is vector 2w, and we can see that it's got components -4, +8, but we can see, because they're algebraic vectors, it's the same thing as 2 times vector w if you just think about being able to distribute or multiply the x component by 2 and the y component by 2. So vector 2w is vector -4, 8. So again, we could use that same reasoning and thinking that vector -3w is going to be vector 6, -12. Okay, and then if we think about if vector w is -2, 4, -3 vector w's, so we're going to have the opposite direction, but 3 times, so we're going to go right 2, down 4, 1 starting from here, right 2, down 1, 2, 3, 4 one time, then right 2, down 1, 2, 3, 4 again, then right 2, down 1, 2, 3, 4 again, and that's going to be vector -3w, just from our geometric sense of vectors. So that's vector -3w, but if we look at that endpoint there, it should be +6, -12. 1, 2, 3, 4, 5, 6, -5, -10, -12. And then, so that says if a vector has components u1 and u2, and you multiply it by a scalar k, then that vector would be ku1, ku2. So you just multiply each component by the constant out front, and it extends right into 3 space as well. So if vector u is 6, -1, 4, vector v is 1, -3, 2, and vector w is 4i hat plus 2j hat plus k hat, then find each of the following. So the first thing I do if I see a question like this is if I see a vector written as scalar multiples of I hat, j hat, and k hat, I just rewrite it in ordered triple form because it's easier to work with. So I just rewrote 4i hat plus 2j hat plus k hat to ordered triple 4, 2, 1 vector. All right, so first we're going to find vector v plus w. So vector v is 1, -3, 2, plus vector w, which is 4, 2, 1, which is vector 1 plus 4 is 5, -3 plus 2 is -1, 2 plus 1 is 3. And it's a vector. That's my answer. So now 3 vector v's. So I'm looking at vector v and I'm going to multiply each component by 3. So 3, -9, 6. So this vector right here is 3 vector v. Okay, so that vector I just wrote down is 3 vector v. And I'm going to subtract 2 vector u's. So here's vector u, and I'm going to multiply each component by 2. So that's going to give me 12, -2, 8. So this vector here is 2 vector u's. And then I'm going to subtract 3 vector v's minus 2 vector u's. And I'm going to do that using that I can subtract each component. So 3 subtract 12 is -9. -9 subtract -2, so I'm subtracting a negative, so I'm adding, it's -7. 6 subtract 8 is -2. So that's vector 3 vector v minus 2 vector u. U plus v plus w, so vector u is 6, -1, 4, plus vector v, which is 1, -3, 2, plus vector w, which is 4, 2, 1. So I can add them by adding their corresponding components. So 6 plus 1 is 7, plus 4 is 11. -1 plus -3 is -4, plus 2 is -2. 4 plus 2 is 6, plus 1 is 7. So there's vector u plus v plus w. Now I've got -3 times vector u minus 8w, in brackets plus 4v. So we can use some vector algebra here to simplify first. So I might do this. So negative 3 vector u plus 24 vector w plus 4 vector v. And now I'll write them down. So this first vector is going to represent negative 3 times vector u. So I'm looking at vector u and multiplying each component by negative 3. So that's going to give me negative 18, positive 3, negative 12, plus, so now the next vector I write down is going to represent 24 vector w's. So I'm looking at vector w and I'm multiplying by 24. So 24 times 4 is 96. 24 times 2 is 48. And 24 times 1 is 24. And then my last vector I write down is going to represent 4 vector v's. So here's vector v. 4 vector v's is 4, negative 12, 8. And I'm adding them. So my first component is going to be negative 18 plus 96 plus 4. You can see there's lots of operational stuff happening here, so there's lots of places that you can make little mistakes. So I would always double check my calculations. And then negative 12 plus 24 plus 8 gives me 20. So that's vector negative 3 times u minus 8w plus 4v. Now we have the magnitude of vector 2u minus v. So again, communication-wise, so I'm showing that I'm finding the magnitude of vector 2u. So vector 2u, put this back in the screen here, I'm multiplying each component of vector u by 2. So that's going to be 12, negative 2, 8, minus vector v, which is 1, negative 3, 2. And we're finding the magnitude of it. So now we're finding the magnitude of, so 12 minus 1 is 11. Negative 2 minus negative 3 is positive 1. 8 minus 2 is 6. Magnitude of it, so square root of 11 squared plus 1 squared plus 6 squared. So now I don't have the magnitude bars anymore because I'm actually doing the magnitude calculation here. And then that's going to be 121 plus 37, square root of 158. So the length of that vector would be the square root of 158 units. And then v hat, we know that that's vector v over its magnitude. So vector v is 1, negative 3, 2 over the square root of 1 squared plus 3 squared plus 2 squared. So that's going to be square root of 14. And then we would write it in ordered triple form as 1 over the square root of 14, negative 3 over the square root of 14, 2 over the square root of 14. And we know it's a vector because we have that ordered triple notation. So there's vector v hat. Okay, and then G, the magnitude of 3w plus 2v minus u. So again, I want my magnitude bar, and then this first vector I write down is going to be 3w, remembering that that's w. So 3w is going to be 12, 6, 3, plus 2v's, which is going to be 2, negative 6, 4, minus vector u, which is 6, negative 1, 4. All in magnitude bars. So that's going to be vector 12, 14 minus 6 is 8. 6 and negative 6 is 0. Minus negative 1 is positive 1. 3 plus 4 is 7. Minus 4 is 3. And then we want the magnitude of that vector, so it's the square root of 8 squared plus 1 squared plus 3 squared, which is the square root of 74. And the magnitude of w hat, that's a trick question because w hat, we could go through all of the steps of finding vector w hat, but we don't need to because it's a unit vector. And we know that the magnitude of any unit vector is 1. Okay, so there's a little application here. If OAPB is a parallelogram, use vectors to find the coordinates of P and then also find the magnitude of OP. So if something's a parallelogram, we know that its sides are equal in length and parallel. So we know, for instance, that a vector OA, so starts at O and ends at A, is going to be exactly the same as vector BP. So that's a vector statement that we can make, that vector OA is going to be identical to vector BP because they have exactly the same magnitude and direction. Well, we know vector OA, or we can find it by doing A minus O. So vector OA is going to be A minus O, which is, because we're subtracting 0, just 1, negative 5, 2. Vector BP, though, we don't know the coordinates of P, so we could say that they're x, y, and z. So we could say that vector BP was P minus B. X minus negative 3 is x plus 3. Y minus 4, we can leave as y minus 4. Z minus 4. So if we set these up equal to each other, vector OA being 1, negative 5, 2, and vector BP being x plus 3, y minus 4, z minus 4. We can see that the corresponding, because they're equal vectors, these components have to be the same because they're equal vectors, so they have to have the same x, y, and z components. So that means that 1 has to equal x plus 3, which gives us a little simple equation that tells us x has to be negative 2. So if we're looking at point P here, we know the x has to be negative 2. We also know that negative 5 has to equal y minus 4, which tells us the y value of point P should be negative 1. And we also know that 2 has to equal z minus 4, which means z has to be 6. So we now know point P. So therefore, point P is negative 2, negative 1, 6. We also have to find the magnitude of OP. So that's the vector from the origin O to point P that we just found. So this vector here. So the magnitude of vector OP is going to be the magnitude of the vector. So we subtract, negative 2 minus 0 is negative 2. Same thing here. But now we want to find its magnitude, which is the square root of 2 squared plus 1 squared plus 6 squared, which is the square root of 41. So there's the magnitude of vector OP. All right, and that is our lesson. So make sure you can write an algebraic vector as either an ordered pair or triple and in terms of I hat, j hat, and k hat, two different notations. Find a unit vector given an algebraic vector, add and subtract algebraic vectors, and find the magnitude of the sum or difference of algebraic vectors.